Alright, this video is going to look at some more examples using the fundamental theorem of calculus. And our first example you'll see that we have here is the integral of x minus x squared divided by 2 times the cube root of x dx. And our limits are -8 to -1. So keep in mind all of those integration techniques we had talked about before with the indefinite integrals are going to be the same thing we're doing for the definite integrals, except for now we just have to evaluate our lower and upper limits. So to start out with this example, I would suggest to rewrite this in a form that we can handle. And to do so, there's one thing we can do here. Notice we have this 2 on the bottom. We can leave it there, or we could actually take the 2 because this is a constant multiplier, and because it's on the bottom, we could take this 2 and move it out front as a 1/2 multiplier. And I think I'm going to do that for this example so you can see how that will work. And then we have x minus x squared on top, and the cube root of x, we could write that as x to the 1/3 power. Okay, and now I want to split this up into essentially 2 fractions here. So we would have x over x to the 1/3 minus the x squared over x to the 1/3, because x to the 1/3 is really our common denominator. So really what I'm trying to do here is I want to divide this x to the 1/3 into both pieces into the numerator. Oops, I'm sorry, this should be -8 to -1 here. So our limit is -8 to -1. And if we do so, x over x to the 1/3, keep in mind the exponent here on the top is understood to be a +1. So therefore, if we divide, we subtract our exponent. So 1 minus 1/3, we would be left with x to the +2/3 minus 2 minus 1/3. So that would be 6/3 minus 1/3, which would be x to the 5/3. And if you notice while we're doing this, we now have this in a nice form that we can easily integrate. So we'll continue to bring down our 1/2, integrating from -8 to -1. And now we can integrate this. And since this is actually in form to integrate, we can drop out the integral. And again, that's a common mistake. We're going to actually integrate. I have students who will leave the integration symbol here, but when you're integrating, once you do that, your integral sign disappears. So this is now just 1/2 multiplied by x to the 2/3 becomes add 1. So that would be x to the 5/3. And keep in mind now we're going to have to divide by 5/3. Now to save you a little bit of work, what I usually like to do here, instead of dividing by the 5/3 like this, well, if we're going to divide by 5/3, remember that means we're going to multiply by the reciprocal. So this 5/3 would come up and we would multiply by 3/5. So I'm going to write this as x to the 5/3. And again, dividing by 5/3 is the same as multiplying by the reciprocal, 3/5. Minus x to the 5/3, so we can do the same thing, but we increase the 5/3 by 1, and we get 8/3. Dividing by 8/3 multiplied by the reciprocal, we get 3/8. And we have our limits. Don't forget, we don't worry about the plus c. We have -8 to -1. So keep in mind now the order is we're looking for f of b minus f of a. So for us that's going to be f of -1, the upper limit, minus f of -8, the lower limit. Now notice we took out this 1/2. I'm going to keep on bringing down our 1/2, and this is going to be multiplied at the very end after we find f of b minus f of a. So at this point, we're going to go ahead and plug in our limits of -1. So I'm going to have 3/5 times -1 raised to the 5/3 power minus 3/8 times -1 raised to the 8/3. Okay, then it's going to be all of that. All right, so now all we have left to do is we need to look at calculating the lower limit. So we're now going to substitute in the -8. So we would end up with 3/5 times -8 raised to the 5/3 power minus 3/8 times -8 raised to the 8/3 power. And that's going to give us our f of a. And of course, all of this then is still multiplied. I'll put the big bracket. We have multiplied by our 1/2 out front. So once again, I'm just going to continue to bring down the 1/2. And as far as the simplification here, you could enter this into your calculator. And at this point, for the simplifying, to make sure you perform the steps right, I'll go ahead and tell you this part should be a -3/5 minus 3/8. And then over here, you should end up with a -96 over 5 minus 96. And if we continue to bring down the 1/2, and then inside here you would end up with a -39 over 40. And of course you could do this in one step with your calculator, minus a -576 over 5. So I know by doing it this way it makes it look like we're doing it this way, I know it looks like we're doing a lot more work than we really are. So we'll continue to bring this down. And we have the -39/40 minus a negative, so that will turn into plus. And you should get 4,569 over 40. And you'll notice a lot of times your book or on the assignment you may see large fractions, but you could certainly use a decimal here. So if we multiply this out then times the 1/2, we would end up with 4,569 over 80. Now, I know that seems like a whole lot of work, and some of it is, but just keep in mind that this is a lot easier than going through that whole limit process that we had looked at in previous videos, where we had to look at the limit as n went to infinity. So here, from integrating this, our answer turns out to be 4,569 over 80. All right, our next example here, we involve our trig functions. And for this one, we have the integral of 1 minus the sine squared theta over cosine squared d theta. Our limits are from 0 to pi over 4. And remember, we don't have a quotient rule, so how do you think we can rewrite so we can integrate this 1 minus sine squared over cosine squared? Well, if you recall, we can simplify the 1 minus sine squared because we know, or hopefully we know, sine squared theta plus cosine squared theta, one of our Pythagorean identities, equals 1. So that means that 1 minus the sine squared would be equal to cosine squared. So all of this here will go to cosine squared theta over cosine squared theta. And hopefully you notice something's going to happen here that's going to make your life really easy. That's going to cancel out to 1 d theta. So now your integration becomes really easy because we can simply integrate this. And I know for some of you, you're going to get confused and say, wait a second, we don't have a variable. But technically, you could think of this as 1 times x to the 0 power. So if we're going to integrate, then that would become x to the first power divided by 1, and I made a mistake here. I used the variable x, and our variable here should be what? Since it's d theta, this would be like saying 1 times theta to the 0 power. So when we integrate, that would be theta to the first power divided by 1, which really would just simply be theta. And there's no plus c because we have to put in our limits from 0 to pi over 4. So if we plug pi over 4 in for theta, we get pi over 4 minus, plug in 0, pi over 4 minus 0 equals pi over 4. So there's our answer. Now let me go back and show you another example here with this integral. I know some of you probably are a little confused. Don't forget, if we had the integral of just the integral of dx, and there's nothing here, this is understood to be the integral of 1 dx. So if you're integrating here, like I had mentioned earlier, this is x to the 0. So all you're doing now is increasing this exponent by 1, so you're getting x to the 1 divided by 1, which is just x. Okay, so keep that in mind. I know sometimes you get a little confused if you don't see a variable, because if you recall, if we had x squared, or if we just simply had x dx, your exponent is a 1, and to integrate we increase it by 1, so that's x squared divided by 2. And of course for these two examples, these are indefinite, so I should have a plus c because there's no limits. All right, so here's 2 more examples to help you out with calculating your definite integrations using this fundamental theorem of calculus.